Simple harmonic motion has a lot of parallels with circular motion. In this little animation here, we can see we've got the trolley that is going to oscillate backwards and forwards about an equilibrium position. And those oscillations are going to yield an extension or a displacement from the equilibrium position. That's going to be mapped on this displacement time graph here, which, as we saw before, is a cosine function. But at the same time, we're also going to map the vertical displacement of a particle undergoing simple harmonic motion here. And you'll see, as we run the video, that our oscillating system matches, in terms of displacement, our circular motion system. Now, this allows us to derive some equations for working out some of the features of an oscillating system. If you can imagine that you were to project a pendulum moving backwards and forwards, and also starting from the same displacement from an equilibrium position in the middle here, a little blob of, say, blue tack that's on a revolving turntable, the two would move backwards and forwards in harmony with each other. And the velocity of the ball is equal to v squared over r. Sorry, the acceleration of the ball is equal to v squared over r, or the force that is pulling it towards the centre of the circle, which in terms of our pendulum is the equilibrium position. That acceleration is given from circular motion equations as v squared over r. And the velocity of a rotating object in circular motion is 2 pi rf, where 2 pi r is our circumference, or the distance it travels in one full revolution, and f is the number of revolutions per second. So that gives us our velocity. Now, since a is equal to v squared over r, if I take my 2 pi rf, and I square it, I get 2 squared, pi squared, f squared, r squared over r. That r is going to cancel with one of these squared r's, and that gives me an equation for the acceleration of 2 pi f squared from here times r, or the radius of the circle. But in terms of our shadows here, that radius is the same as my extension, or my displacement, of my pendulum. And so as a result, my acceleration equation becomes, for any object undergoing simple harmonic motion, the acceleration is equal to minus, because remember, of course, that the acceleration always acts in the opposite direction to the displacement, minus 2 pi f squared over x, where once again that there is our SHM constant. That there is our displacement in meters, unless you're asked for something else. And that does prove that an object in simple harmonic motion undergoes motion with acceleration is equal to minus a constant times x. They are directly proportional. Remembering, of course, that we get our displacement time graph that we saw beforehand. The actual function that is mapped by this is that x is equal to a cos 2 pi ft. Now, it's worth remembering this because they might give you a displacement time graph, and from that you can work out, from f is 1 over t, what f is. Well, t you can read off the graph. Once you've got that, they might tell you how far into the oscillation you are, and as a result, you can actually work out what your displacement is at that time t, because from the graph you can read off the time period. And the last thing to point out is you should always have, for this kind of calculation where you're doing a cos function of something that's in radians, you'll calculate it in radians.